Yeah. Okay, now we're recording. And I really hope it records my share screen rather than just my face. We'll see. Okay, and so then at the very end here, right, this is telling us something about those energy levels. And so this is 1 over the final energy level squared minus 1 over the initial energy level squared. I'm not planning on doing a lot of doing a lot of plug and chug in class. You know, I hope you know how to fill in some constants. And really I like this textbook a lot for chapters past 4. These first few chapters is not how I would write a textbook. And so it's a sort of a broad overview of everything we're going to learn, but it's a pretty in-depth explanations, right? Like the Rydberg equation, and it talks a little bit about particle in a box. It talks about the harmonic oscillator. It goes deeply into some of these topics, and then we come back out and we talk about instrumentation. The way I would think about a textbook is to, bring up those topics as we need them rather than as introduction, because they're not really surface level topics. I don't know if this book sort of imagines that everybody has had Pekin 2 or what, but in any case, I'm not going to go too in depth for these first couple of chapters. Chapter 1 and chapter, as I didn't lecture at all on chapter 1. Chapter 2 is a lot of this, how does light interact with matter, which is an important piece, but I'm not going to delve too deeply into the quantum mechanics of it. So here's the Rydberg equation. We use this to find the difference in energy levels. What those look like, right? Remember, it's quantum mechanics. And so here is this Bohr model of a hydrogen atom. And we have our different energy levels. Remember always that the lowest energy level is the closest to the nucleus, right? And so energy level 1 here is the closest one to the nucleus, and then it increases as we get further away. The other thing to keep in mind is that for this system of a nucleus and its electron, we consider it to be 0 energy when there's no interaction between those two whatsoever. And so that is essentially when they're infinitely apart. And so if we look at this energy graph, 0 is way up here at the top of the scale, and the values get more negative. More negative because it is more favorable, it's lower in energy for a positive nucleus to have a negative electron around it. Right? And so the lowest energy level for the electron is going to be that energy level where it can be as close as possible to the positively charged nucleus. This negative 13.6 eV is for hydrogen. But we have our first energy level, and then of course we jump up here to our second energy level, third, and you notice that these energy levels get closer and closer together. We'll talk a little bit more about that, especially in terms of vibrations. But again, I don't want to get deep into the quantum mechanics. If you've had Pekin 2, you know why this happens. If you haven't had Pekin 2, you probably don't care. These electronic energy levels get closer and closer together as we get further and further away from the nucleus. And here you see this little blue electron. He's going down from n equals 3 to n equals 2. And in that process, he's likely going to give off a photon. I used a shorthand for photon. It's always going to be a wiggly line. And then since energy is h times nu, I'm always going to label that photon as h nu. And so that's the shorthand for a photon coming out. Right. With quantum states, right, what do we think about when we think about quantization? What does it mean to be quantized?
Like a discrete number.
Yeah. Here's our math terms. Yeah, when we talk about quantization, we're talking about something with discrete values, with known values. If we're talking about something that is equally quantized, unlike a hydrogen atom, we can think about stairs, right? You can be on the top stair, you can be on the first stair, you can be on the second stair, but you can't be on the 1 2/3 stair, right? Your foot will just fall down to the next stair. And so you can't have, you know, our electron can never exist in this position. It can only be at n equals 2 or n equals 1. It can't be here at n equals 1.5. And so when we think about quantization, we have these discrete values. For all these quantum states, we're going to have both electronic quantum states, like this one. We're going to have vibrational quantum states. We're going to have rotational quantum states. We're going to have nuclear quantum states, right? Every different type of interaction will have its own quantum states. And so we'll have electronic, we'll have vibrational, we'll have rotational, and we have nuclear. Okay. And then there are some sort of combined quantum states. You can talk about rho vibrational, or there's a really weird term for one that incorporates all three. It's like rho vibratronic or something. It sounds like a made-up sci-fi word. But for each of these types of quantum states, we have different ways of measuring them. Who knows roughly what kind of photon do we get out for an electronic transition? What wavelength range? What part of the electromagnetic spectrum?
Visible light.
Yeah, absolutely. And so when we talk about electronic transition, the instrument we're going to talk about is a UV vis, right? Those energy gaps in an electronic energy levels are pretty large, and so UV light is actually pretty energetic. And so when we think about electronic, we're talking about UV vis. How about vibrational? What instrument do you think we might measure vibrational transitions with?
IR.
Absolutely. We just named the instrument IR. And I'm going to label it an FTIR for Fourier transform. Again, that's part of chapter 2. Fourier transform is not chapter 2 material, in my opinion, but it talks a little bit about Fourier transform. For rotational transitions, these are very low energy, right? But they're still meaningful, and they still contribute to the overall energy of the molecule. We measure these using microwave spectroscopy. This is what my wife did her PhD thesis on, microwave spectroscopy, rotation of molecules. And then where do we look at nuclear transitions? Or how do we look at nuclear transition?
Is that NMR?
NMR, absolutely. And NMR stands for nuclear magnetic resonance. We will discuss that much more later in the semester. Right? But each of these sort of types of energy transitions corresponds not only to a different instrument, but to a different region of that electromagnetic spectrum. If we had one instrument that could measure everything, that'd be great. It'd have a very broad what? We talked about Monday. If it covers a very wide range.
Dynamic range?
Yeah, it has a huge dynamic range, right? So UV vis, we're talking about, 400 nanometers at the bottom end, even lower if it's UV, all the way up to microwave, which is, if we're still talking about nanometers, from 400 nanometers up to 4 million nanometers, right? I mean, so that would be a huge dynamic range. And we just don't have an instrument that does that. Okay? All right, so just a tiny, tiny bit of how we label quantum states so that you know exactly what's happening in our Jablonski diagram. When we talk about electronic states, we're going to talk about the multiplicity of those states. And the multiplicity is given by the equation 2s plus 1. What does that little tiny s mean? Well, s is our spin quantum number. Right? And so if I have, I'm going to draw a couple of different situations here. This is not what I want to do. Right? So if I have both electrons like this, right? We call those we call that being in the ground state, right? It's in the lowest energy state. Okay. And the total spin for this system, these two electrons, the total spin for this system is 0 because I have a plus a half for one and have a minus a half for the other, right? And so little s is 0. And so my multiplicity is 1. 2 times 0 plus 1 is 1. So my multiplicity and when my multiplicity is equal to 1, I call it a singlet state. Right? Makes sense. 1 single. And we represent that with a big old S. Right? Because it's the ground state, the lowest energy state, I'm going to give it a 0, like a little sub-0, so that I know that it's the lowest energy state, the lowest possible singlet state. So these two are both going to be excited states. And I have this one first. And so one of those electrons, nothing happened to it except it got promoted into a higher energy level. And so what's the multiplicity for that system, the middle set of electrons? Did any of my spins change?
Still 1.
My spins didn't change. So S is still 0. We label this one S1 because that is the next lowest energy singlet state, right? It's just going up to the next energy level. If I had drawn several more energy levels above it, we could talk about S2 and S3, etc. The last option is where not only do I gain energy, but also I do a spin flip. Right? And so now, what's the total what's the total spin for this system? I have a positive half and another positive half, so that's a
Whole.
whole. Yeah. And so my multiplicity, 2 times 1 plus 1, is 3. And so we call that not a singlet, but a triplet. And so we call that a T. Even though this is the lowest energy triplet state, because we can't have two electrons with the same spin in the same orbital, we don't consider this a ground state, right? This is still an excited state because not all the electrons are in their lowest energy level. And so this is the first excited triplet state. Right? And so we have S naught, S1, and then T1.
Dr. Davis,
Yes.
what's the S value on the triplet state?
Yeah, so for here, S is 1 because we have plus a half for the bottom
Okay.
electron and plus a half for the top electron. They don't cancel out.
Okay, thank you.
Yep. All right. The other thing that I just want to say really quickly is that for vibrational states, our textbook uses n, lowercase n. That's real weird to me. I'm used to seeing it as either just a straight V or the Greek nu, right? And of course, n and nu are the same, but the same letter. But in any case, if you see any of these in an energy level diagram, they're most likely referring to vibrational states, right? Vibrational states are much lower in energy than electronic states, and rotational states are even smaller in energy. And so we really don't tend to label rotational states when we're looking at electronic states because the difference in energy is so small that it really doesn't affect that overall energy a whole lot. Okay, so moving on to the main event for today. Questions about that stuff? Finding multiplicity, finding the, this is called a term symbol. You inorganicers will learn all about that too. All right, the Jablonski diagram. Bum, bum, bum. So for the Jablonski diagram, this is intended to show the variety of transitions that we can have in an atom or a molecule rather than atom. It gets pretty complicated. And if I were in the classroom, I'd draw the Jablonski diagram on one side of the whiteboard and talk about it on the other side of the whiteboard, and you can see everything at the same time. I can't do that here. So I'm going to draw it, and I'm going to jump back and forth. Okay. So the first thing we want to draw in is our ground electronic state, our S naught. And of course, that's relatively low in energy, relatively speaking. A bit higher in energy. I'm not going to draw it all the way across, but there's our S1. And S2, is it going to be equally spaced? Farther away, closer? Closer. Yeah, so S2 is going to be a little closer to S1 than S1 is to S0. That triplet energy state is going to be somewhere over here. The energy for that guy is not all that different from our singlet state, and it depends on the molecule. Sometimes it's a little bit lower in energy, sometimes it's a little bit higher in energy, but generally speaking, it's about the same energy. Okay. Now, for each of these, I'm going to switch colors here. For each of these, we're going to have some vibrational energy levels as well. I wonder if I can use a ruler on my drawing tablet here. Let's see. So,
Ooh, that's nice.
isn't it though?
Mm-hmm.
I'm not going to draw in all the vibrational energy levels, but there's a few. And it's true that just like the electronic energy levels, the vibrational energy levels will get closer together as they get higher order. And so eventually they just become too close to draw separately. Uh-oh. There is an image in the text if you'd rather just look at it, but I think drawing it out is meaningful. I'm going to follow our text notation and call these in, even though that's not what I'm used to, but there is an overlap here. At the very ground state, right, there is a vibrational level there. And so that one is 0. Then we have 1, 2, 3, and 4. Am I just writing so small you can't see anything, or is it reasonable for you?
It's good.
Okay. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Right. And so again, that 0 overlaps with the black electronic energy level in each case. All right, so that is, these energy levels exist in every molecule, even if they're not populated, right? They still exist based on the electronic structure of a particular molecule. And so we have different transitions. The first transition is a transition from S0 up to S1, right? And I'm going to draw in a couple of these for the reason that at room temperature, it's very unlikely for all of the molecules to be in the lowest vibrational energy state, right? Remember, temperature is just a way of thinking about vibrational energy. And so the warmer something is, the more vibrational energy it has. And so as we have these transitions, it's unlikely that all of our molecules are in the ground state. It's also unlikely that all of our molecules are going to go exactly into the ground state up above. And so I could draw tons of different combinations of lower level vibrational state, upper level vibrational state. If you took PChem2, you know what the selection rules are for vibrational transitions, right? I'm not worried about it here. Just know there's lots of them. Right? These, of course, are absorptions. And we can have some absorptions that go from the S0 all the way up to the S2. It's not uncalled for. It's just not as common because it requires more energy. And so those are our absorptions. Okay. And so I'll go back to the Jablonski in a minute, but when we talk about absorption events, right? Absorbing, what are we absorbing really?
Energy.
What?
Energy in the form. Do you absorb a photon?
It could be a photon. It could be anything. It could be heat, right? It could be chemical energy if we're talking about chemiluminescence. It could be lots of different things. And so energy is a nice broad term. And so we are absorbing energy, right? And just so that we have all that on paper, this could be a photon. This could be heat. This could be chemical energy. Right? When we think of a photon, of course, think about something like a UV vis. When we think about heat, think about a flame test. Right? And then when we think about chemical energy, think about a firefly. Right? All of those things cause an electron to get excited. And these absorption events happen from many ground state S0 vibrational levels to many S1 vibrational levels. right? And because of this multitude of transitions, that's why we have such broad peaks in our UV vis, right? When you look at a UV vis, it's not one nice transition, like one energy. It's sort of this broad, you get these broad peaks in UV vis, right? And the reason is that, maybe this energy corresponds to S naught in 2 going to S1 in 0. I don't know exactly, but maybe that's what it looks like. The one that's a little bit lower in energy, right, is over here, and there's another one over here that's a little bit lower in energy, another one here that's a little bit lower in energy, one here that's a little bit higher in energy. I said those backwards. These are lower in energy because they're higher wavelength. These over here are lower in energy. These here are higher energy. But because they're because they're at room temperature and there's lots of different vibrational levels that are occupied by these molecules, we don't get just a single transition. If I go back to the Jablonski diagram, right, if we were to go on this first absorption that I didn't draw with a ruler, from S naught in naught to S1 in naught, right, that's just one energy. We would see a single wavelength absorption. We wouldn't see this broad peak. That was actually my PhD work. We cooled molecules down to about 10 Kelvin and then took their UV spectrum to see what their lowest conformation was, their lowest energy structural conformation without having to worry about all those vibrations. Okay. And so those are the absorptions that we see in a molecule. And again, that covers, that covers both electronic and vibrational absorptions. Because we're talking about electronic absorptions, I'm not going to talk right now about just staying within the S naught and going from N0 to N2 or N1 to N4. We'll talk about that when we talk about IR. But generally speaking, for an electronic system, that's what we are looking at. Okay. Now, once our electrons have been excited to these excited states, what are they going to do? Well, the first option, and an option that occurs in almost every case, is that it's first going to relax as quickly as it can. And the number one way for a molecule to do that is to just start vibrating. Right? That's its way to get out energy. And so this tallest transition I have here, right, he's in the N equals 3 or N equals 4. I didn't draw a very exact arrow. But what's going to happen is he's going to get rid of some energy by just losing energy to vibration, right? He's going to essentially get his wiggles out and lose enough energy that he goes from an excited vibrational state to a lower vibrational state. This guy up here too can do that vibrational relaxation. And so depending on how close your S2 and your S1 are, right, if they are, as you get closer and closer, as you get higher and higher in energy, those energy levels get closer and closer. It's possible that you could have some vibrational relaxation from the S2 in the ground vibrational state to the S1 in a very high excited vibrational state. Right? These are all possible. And so in orange here, we have vibrational relaxation. Right? We also have a method where this S1 N equals 2 is the same energy, as my T1 N equals 0. Right? And it is possible for a molecule to convert from S1 N equals 2 over to T1 N equals 0, right? Don't write that exact transition down because it's different for different molecules, but generally speaking, from the S1 to the T1. And so this conversion is called intersystem crossing. Okay? From the singlet system to the triplet system. Okay? And all of these fall under this non-radiative events, right? We don't get a photon back out when any of this happens. And so the two non-radiative events we have are vibrational relaxation which is either from a high N to a low N, or from N equals 0 in a high S. When I say high S, you know what I mean? A high excited singlet state to N equals big number. I'll just say 100 in a lower singlet state. Right? And of course, as soon as it's in that lower singlet state, in 100, it's going to vibrate back down to low N, but stay in that same singlet state. And so vibrational relaxation, we can convert between both either just vibrational states or sort of a combination of vibrational and electronic states. Okay. The second option for a non-radiative event is this intersystem crossing. Where we go from an S1 to a T1. Classically, this is a forbidden transition. Right? But we're not talking about classical physics, we're talking about quantum physics, and strange things happen in quantum physics. And so even though this is forbidden, it does happen, but it happens at a very, very low level, right? This is not a common occurrence. For some types of molecules, for some materials, it happens more often. But generally speaking, it's not a very common occurrence. Okay. All right, going back to our Jablonski diagram then, the last piece of the puzzle to add are the, of course, radiative events, right? And so if we look at the Jablonski diagram, we could have, so once our excited state molecule has done its vibrational relaxation, he's likely in the ground vibrational state of that excited electronic state. The wording can get confusing, right? And then he's going to go down in energy to some ground state, ground electronic state, even if it's an excited vibrational state, right? And again, just like you get lots of different absorptions, you get a lot of these different emissions. Okay. Over here in the T1 to the S naught, we can do this too. Okay. These emissions have different names. They're different processes because one is singlet to singlet, the other is triplet to singlet, right? When we think about something giving off light, we often talk about that as fluorescence. Right? And that is, of course, the most common way of doing something. If we have a T1 to S0 transition, that is associated with phosphorescence. How many of you had glow-in-the-dark stars on your ceiling as a kid? Or perhaps still have glow-in-the-dark stars? No judgment. Nobody? I don't see a single hand. I had glow-in-the-dark stars when I was a kid. Yeah. Glow-in-the-dark hands on your wristwatch? I don't know. So all of those things that glow in the dark are phosphorescent materials, right? They're materials that are very good at that inter-system crossing. And so essentially a lot of molecules are stuck in that excited triplet state. And because it's a forbidden transition, they don't convert, they don't go from T1 to S0 very quickly, right? We have a slide for me to write all this down. So emission events. The first and the most common is fluorescence. Right? This is a singlet to singlet transition, right? And it is most commonly S1 to S0, but of course you could have it between any two singlet states. Singlet to singlet transition, and fluorescence has a pretty short lifetime, right? When we talk about a quantum lifetime, it's essentially how long it takes for that particular transition to occur. When you turn on a fluorescent light bulb, right, it starts pretty quickly. When you turn off a fluorescent light bulb, it's also off pretty quickly, right? It doesn't linger a whole lot. And so generally speaking, when we talk about short lifetimes, we're talking about anywhere from the range of 10 to the minus 12 seconds all the way up to 10 to the minus 3 seconds, right? And so these can be really fast transitions, or they can be just sort of fast transitions, right? A millisecond is still a pretty short period of time.
Dr. Davis, so you said that's like how long it takes for the fluorescence to start?
It's essentially, think about it as how often a molecule will change from an excited singlet state to a lower singlet state, right? How quickly does that transition occur?
Okay.
And the third bullet point I'll just add here, even though I've said it, is this is the most common. Right? The second is phosphorescence. Right? This is from a triplet to a singlet. And remember that this is forbidden. Classically. Okay. Spin flips in general are a forbidden thing. And so because of that, this takes a much longer time right? And so 10 to the negative 6 all the way up to 10 to the positive third seconds, right? These can take a really long time between events. If you had glow-in-the-dark stars on your ceiling, right? You know that you cut the light off and they would stay somewhat glowy for like an hour or something. And so just based on the material, based on what the population is in that excited triplet state, you're going to have different lifetimes for that phosphorescence. Okay, so that completes our Jablonski diagram. We have those three categories of transitions, and then just knowing where those different excited states are. Right? The last slides on this handout are the homework. I don't know if you read the syllabus yet. I posted it yesterday. I do homework a little differently in this class. I assign homework throughout, and then on the day of the exam, I expect you to turn in your homework. about 10 to 15% of the homework of the exam will be exactly homework problems, right? So you don't have to do them on the exam if you have your homework, right? Because you've already done them. Turn in your homework. The other side of that coin is you don't have to do your homework. You can do that extra 10 to 15% on the exam, right? But the caveat is if you've done on your homework, I'll give you partial credit. If you do it the day of the exam, no partial credit will be given, right? So you better know your stuff. So the three questions, one from chapter 1 and a couple from chapter 2. The chapter 1 stuff is just review from 214. Chapter 2, both of these deal with vibrational transitions, the Morse potential. And while I didn't talk about it today, it's really just a plug and chug kind of equation. I want you to see it a little bit. 2.3 is just a simple use of that equation. 2.5 is Excel. It just helps me see your Excel skills and so that you know, I know what you can do with it, okay? All right, I've run a little long, I apologize.
Thank
See you,
you.
Dr. Davis.
So long.
Yeah.